So I hand over to Ashwat sir for the session. Ashwat sir, you can continue with your session.
Thank you, Satyan sir. I hope you can hear me.
Yes, you are audible, sir. Loud and clear.
I am at Manipal Institute of Technology, Bangalore. On, so I am at the event. The network
Okay.
is their network, so sometimes some kind of hiccups will be there. So I apologize for that, and I request the participants to bear with me. Right in between disconnection, please wait. So then immediately it connects. So if there is something you people can't hear or anything, you please put up the chat message on the chat message. Okay, right. So we can start the today's session. Very good afternoon to all the participants. Pili sir is here. So, sir, Pili sir, any announcement you want to make?
I reached a little late, so I requested Satyendra to just say, yeah, please, we can start. Yeah.
Yes,
People
sir.
will join anyway, so we can. Right. Thank you. Okay, Satyendra. Yeah.
Yes, sir.
Yes, sir. Yes, we can. Okay. Right. So I'll shut down my video as well because for the video, sorry, for the presentation and the audio. Yeah. So let me share my screen. I'm just sharing. Wait a minute. It will take some time. Yeah. Okay. So I will. I want to do for today is. So just a minute. I want to discuss about the quantum gates, which are and double qubit quantum gates, right? And then I have to go and discuss about there is a way to realize quantum gates. So that also I would like to discuss for today, right? So let me use my. I'm just projecting something here. I'm projecting sphere representation. Okay, right? So describe what it is, then you will really appreciate what we are doing here. Okay, right? So just a minute. Okay, right. So yeah, the system seriously very slow. Yeah, what I want to discuss is quantum gates. Okay, among that there are two types. One is okay. Anything other single qubit gates is a multiple qubit. Okay, multiple qubit gates. If you want, you can start saying like 2 qubit gates and 3 qubit gates and so on. So the most important gates which we usually come across is single qubit gates and 2 qubit gates. Okay, so there are 3 qubit gates also there. Okay, Oh, yeah, this whatever PPTs, whiteboard notes I was using yesterday, which is so there will be Canva is a platform where you will have your own account. You can access all the material used by resource persons. Okay, that will be done. That's why it is not done shared yet to you people. Please bear with us. The organizers will account so you can access the content there. Okay, qubit gates and multiple qubit gates. Among the multiple qubits, and then 3 qubit. Okay, so which we come across. Okay, and qubit gates are there, which is like advanced. We will not discuss them right. So to understand the single qubit gates, first of all, what is single qubit? It carries. How are we going to? Okay, how are that information using a gate? Okay, yeah. Can you classify quantum gate universal gates? Okay, you mean to say gates? We will definitely do it as we go through this session. Are there NAND gate and NOR gate? So we will compare with that also. Okay, means distinction. The gates are usually distinct classified in terms of single and multiple qubit gate. So we will discuss in detail. Okay, right? And a 3-level system, then I would need 3 qubit system to define how to formulate this problem into qubit. Okay. Okay. Somebody was saying you can't see the black. I said probably the network issue, so just bear with us. It'll show up. Okay. Right. So the single qubit gates are there. So first of all, I need to know what is the state and how I am going to process that. As we also quantum state, which would look like is equal to alpha 0. Okay, alpha 0 ket beta 1 ket. Okay, so this is a quantum. Physically, it can be an electron being in two states, two, or a photon being existing in vertical. Okay, or some of some hyperfine hyper. Okay, right? Okay, just a minute. Okay, just a minute. People can hear me? Hello?
Yes, sir. Yes, sir. Here, whiteboard is also visible. No problem. You keep
Yeah.
your camera off. That should be sufficient.
Yes, sir. Yes, sir. So, could be various ways the quantum state would exist. Few examples, like I said, two quantum state. Okay, that is one. and a photon being in superposition of and vertical polarization. Okay, so the examples. Okay, now process on paper or on some kind of a system. Okay, so I have to represent the information on paper. Presentation would be quantum as a column vector 1, okay, 0 multiplied by alpha plus beta 0, 1 column vector, because 0 get as 1, 0 and 1 get as 0, 1. Okay, so because of that, what is happening is, okay, because of what happening is, hello, yeah, what is happening is quantum state becomes column vector, which is like 2 by 1 dimension. Now the quantum state, whatever quantum state which is represented on paper, must go on to become something else, some other form. Okay, so if at all I have to process, or I would say manipulate it, we have to change the form of quantum state, whatever it is in this form. Now looking at this quantum state, if you say alpha beta column vector, okay, right? So what I can do with this alpha and column vector, you can think about. Okay, so what I want is, I want a quantum information go into some gate, okay, comes out in some other quantum state side. Okay, as of now we don't know whether the output is quantum state or not, let's say that. Okay, right, we don't know that. What we will say, it is undergoing some change. Okay, now undergoing a change mathematically, what it has a column matrix alpha beta. Alpha beta must go on to become something else. Okay, right? So now the quantum state psi, if you notice, it has a very good resemblance to two-dimensional vector r vector. Okay, not only just r vector is actually a unit vector. Okay, the length of the vector is 1 and all the points on the unit circle are represented by this vector. Okay, because the length of r is 1, so all the points on the unit circle, because square is equal to 1. Okay, so similarly alpha absolute square plus alpha beta absolute square is equal to 1. So such a resemblance, as a one-to-one relation is there between the quantum state and a two-dimensional vector. Okay, right? Now, is there a geometrical representation for the quantum state just like a 2D vector? If I ask, yes, there is a nice interpretation, that is called a block sphere interpretation. Block sphere geometrical interpretation, block sphere. How it is going to be done is, alpha is equal to cos theta by 2, beta is equal to exponential I5 sin theta by 2. If I introduce that, what happens? alpha is converted in terms of theta, beta is converted in terms of phi as well as theta. This. Now, so to represent a block sphere, so to represent a quantum state in terms of theta and phi, what one can do, one can take a three-dimensional polar coordinate system. What is that? It has a sphere, okay? Okay, so there is North Pole, there is a South Pole. Take any vector, let's say some point, if it makes an angle theta with the polar North Pole, and if you just drop the vector shadow on the xy plane, that on the xy plane, that shadow will make phi angle with the x-axis. Okay, right? This is a three-dimensional spherical polar coordinate system. One thing we did here is we just confined the radius of the vector. Radial dimension is ignored, which are theta cap and phi cap are the only dimensions which are going to vary in this spherical polar coordinate system. Equal to cos theta by 2, beta equal to exponential sine phi, exponential I phi into sine theta by 2 if I introduce. Now I can represent quantum, okay, as cos theta by 2 0 ket phi sine theta by 2 1 ket. Purpose of introducing alpha as cos, beta as exponential I phi into sine theta by 2 is I can show geometrically on some three-dimensional system where point are constrained to fixed scenario. Okay, so where the r dimension is fixed because r cap is no more varied, it is fixed to some motion. Now, this is how the quantum system is represented. One simple scenario, let's say I take a runs between north pole to south pole. What is the range? It range is 0 to 5. Okay. Implies cos theta by 2 whenever theta equal to 0, right? And at the same time, sine theta by 2 with theta value equal to 0 implies 0. This is the situation when theta equal to 0, I will have quantum state psi is equal to ket. Okay, 1 into 0 ket. I'm sorry, 1 into 0 ket. So sphere, on a block sphere, the north pole is correspond to 0 ket because theta have not varied anything other than 0. So I'll have quantum state presented at the north pole. Okay, right? Now, when I take a theta value is equal to phi, friends, let's see now. Cos theta by 2 is 90, cos 90, which is 0, and it is 1. Okay, so in that case, quantum state at is equal to 1 ket. And by the way, there is an exponential I phi is also there for the beta thing because on a south pole, single point, if you just say, okay, on a single point, you are not going to have any variation. So phi angle is not going to contribute. So On a block sphere, the north pole corresponds to 0 ket. So, okay. So now if you just see, notice the quantum state is pointing towards the north pole for the 0 ket state. Towards the 1 ket for the south pole. Now those are the extreme cases. Theta is taking, I value is extreme cases. Now the question is, what happens theta is any other value, okay, 5. Okay, let me take theta is equal to pi by 2, 90 degrees. In that cos theta by 2, it is cos 45 degrees, which will be 1 by square root of 2. Similarly, what is the sin theta by 2? That is also 1 by the exponential alpha in this case. You know why? Because exponential is coming into the case. Okay, if you just notice, if theta is pi by 2, means the quantity is pointing towards the north pole. It is now moved from the north pole. That means the quantum state can be anywhere in the equatorial plane. Means it can be along the y-axis, it can be along the x-axis, be along the negative x-axis, negative y-axis, or not only that, it is anywhere on the equatorial plane. So what quantum state when theta equal to pi by 2 can be pointing in any direction xy plane. Okay, so any direction on the xy plane, that is initial case quantum state is pointing the north pole when theta 2, so it is moving from north pole on to the equatorial plane. Okay, now the theta can be any direction it can be pointing out. Okay, right? So it can be pointing. Saying board is not visible. Why? Settings. Yeah. Wait a minute. Yeah, I think now screen is visible, I guess. Screen is visible.
Yes, sir. Screen is visible.
I guess. Okay, right.
You can switch off the video, sir. I think some people may have the problem, not you.
Yeah.
We are able to hear you. We are able to see you
It
clearly.
is maybe from my end also. I would
Okay.
not say everything is perfect.
Right.
Now, psi can be pointing in any direction on the xy plane. XY plane means I have another degree of freedom where phi angle which varies from 0 to 2. Okay, so what I mean is on the angle can go 0 to 2 pi. Right. Just a minute. 1 minute, everyone. I just started sharing, but whiteboard is stopped. Yeah.
Yeah, it is now on, sir.
Yeah, the thing is, like, network is just maybe many people being used in this hostel. What I will do, yeah, I will shut down my video so that if it doesn't work, what I will do is,
Sir, it is now visible. You just have to scroll up a little bit.
ha,
That's what they are asking.
yes, sir.
Yeah.
Right.
Able to move the nodes, that will be sufficient. What is visible is psi can be pointing any direction on XY plane.
Yeah.
Take to the next slide. Yeah.
Yes, sir.
It is not,
Up to that point.
it is not yet come to the third slide.
So the theta is varying, sorry, phi varies between 0 to 2 pi. Okay. Okay, then use my PPT as it is instead of just taking. One minute. Even there is a network is seriously problematic. The even mobile network is not working here. Hello everyone, can you see my screen?
Yes, sir.
Yeah. I just only connected my laptop, not the tab. Maybe in that way we can stop too much network usage. Okay, so what I'll do, I'll use my PPT only. Okay, right. So what I want to show here, like I emphasize here is
Sir, maybe you can make it full screen.
full screen, sir.
If
Present slideshow. Now, sir.
yes, sir, better. Yeah, this will be better.
What I want to emphasize here is, if I say a quantum state is pointing towards the North Pole, means it is in the ground state, just only zero ket with a theta being zero. Okay. When theta is zero, there is no notion of pi angle because see theta is zero means single point. If theta is also pi means again single point. Any other point, if see North Pole and the quantum state vector makes an angle theta. So that is the most important thing. Okay, if the quantum state is pointing in the North Pole direction, when I somehow rotate the quantum state, introducing an angle between quantum state to the North Pole, okay, I can increase to what extent? I can increase the angle from 0 to pi by 2. Okay, right? When I increase the angle from 0 to pi by 2, what happens is quantum state, when it is initially pointing towards the North Pole, come back to the South Pole, sorry, the equatorial plane. And now the question is whether it is come back to the x direction, or it comes back to the y position, or it comes back to the negative y or a negative x. That's all depends about state. Okay, right? So now, as of now, in the diagram, what is shown here is a quantum state is rotated about y-axis with an angle of pi by 2. Then what happens? Quantum state becomes equal superposition in 0 ket and 1 ket. So there is a equal contribution coming from 0 ket to 1 ket. Okay, right? So that is called creating a quantum system from superposition state. So this can be done by some quantum operations. And if the quantum state is pointing along the zero ket, means North Pole, I can convert that to become a South Pole pointing vector by just rotating that quantum state from the North Pole to the South Pole. Okay, I have introduced the angle from 0 to pi angle we can introduce. So that qubit gate rotation. I can also rotate all the way from 0 to pi. When it comes to 0 to anything other, quantum state is going to have a contribution from both 0 ket and 1 ket. You know why? For example, if I rotate the quantum state from 0 to pi by 2, it is going to exist on the equatorial plane here. If I increase the quantum state, let's say from 3 pi by 2, not just a pi by 2, some 3 pi by 2. 3 pi by 2 is something like quantum state system completes to 1 pi by pi degree radians and then comes back here. So that is going to be equatorial plane again. So likewise, I can change the angle between polar North Pole and the quantum state. So this is how a quantum system representation and a graph or a geometric block sphere introduce the extra angle. Now this is a geometrical interpretation. Now how can I do it on paper? Okay, right? So now let me show here. Okay, so let me see if there is any chart problem. Okay, hope there is no problem here. Okay, right. So Now, talking about the single qubit gates. Now, keep the idea of rotation at one side. Now, try to see the things from the prospect of processing things on the paper. Okay, I want to represent how things changes. Now, when I recollect a gates means, for me, it's a classical gates. Okay, that is what I was taught at a very early stage. Now, what is a gates? Classical gates for me. The classical gates are, it's a negation operation. A negation operation is something quantum, sorry, any information of high will become low, low becomes high. Means a transistor being in on state can be made to off state. Okay, so depending on the gate to base voltage, all those things, emitter gate voltage difference, all those things that are there in the electronics, that is how you can switch on and off the transistor. If there is an information of high is there, I want to convert to low, I just somehow switch off the transistor so that no information goes out, it becomes a low. Okay, so that is a negation for you, right? So in the case of negation, 0 becomes 1, 1 becomes 0. Let's say if that kind of a quantum gate operation is there, what it will have effect? It will have a effect of 0 ket becoming 1 ket, 1 ket becoming 0 ket. That's a NOT gate operation for you, right? Now, if you carefully look at that, when I have a NOT gate operation on a given quantum state, I'm not saying anything alpha and beta are changing. Only I'm talking about the states of 0 ket becoming 1 ket, states of 1 ket becoming 0 ket. The probabilities, I'm not attacking the probabilities, only the base states I am telling it is being changed. Okay. Now, if you notice, overall state, let's say the final state is psi prime with alpha 1 ket beta 0 ket. When I compare both sides, if I notice carefully, what I see, if I just see, always I try to write a 0 ket first, 1 ket later. But in the right hand side, what happens because of the NOT operation, 1 ket is coming first, 0 ket coming later. So just rearrange. When I do the rearrange, what you see is very interesting. You see the probability amplitudes appear to be interchanged. Means alpha place beta has come, in beta place alpha has come. So it's like, let's say my quantum system of a single qubit supposed to be in the ground state about 60%, excited state about 40% is there initially, let's say. If I act a NOT operation on that, it slightly becomes interchanged. Means excited state becomes 60%, ground state becomes 40%. So that is a NOT gate operation for you when it comes to quantum single qubit gate. Okay, right? So yeah, please, I will be switching between chat messages to the presentation. If there is anything you cannot see, please let me know. Okay, right. Now, fine. Okay, so that is the gate operation. Now, let's say I want to write down in terms of matrix interpretation. You know why I want to bring a matrix interpretation? Because the quantum state is represented as a column vector. Okay, a column matrix, in fact, it's 2 by 1 column matrix. Alpha beta column matrix is becoming beta alpha column matrix. Okay, which means there must be some transformation matrix multiplying onto the alpha beta, pushing alpha beta to become beta alpha. So that is a gate operation for you, or matrix operation for you. Now, by trial and error method, you can easily guess and come up with what could be the transformation matrix could be. That is 0, 1, 1, 0. That is a X gate. It is called a X gate operation. Why I am saying 0 becoming 1, 1 becoming 0 is some kind of a not operation for you here. Okay. Now, interestingly, even on the psi prime, the new state, the probability amplitudes are summing to 1 with the absolute squares. So, the norm of a quantum state is remaining intact. Norm in the sense the length of the state after the processing remains intact comparison to the initial state. So, it is said that the quantum state operations preserves the norms of the quantum states. Means whatever goes into the quantum state, when it is exited, it is remain to be quantum state as it is, but the internal arrangement may take place. Some kind of a rearrangement, some kind of a change may take place, but overall absolute sum square is going to be 1. Overall length is going to be 1. That is what we observed. Okay. Now, looking at the X matrix, we can see the X matrix is not any ordinary X matrix. It is actually called a unitary matrix in linear algebra. What is this linear unitary matrix is, you take a matrix, you multiply that matrix with its own adjoint, you would be going to get identity matrix, that is a unitary matrix. So the 0 1 1 0 is not any ordinary matrix, it's a unitary matrix. Okay, right? So from here you can say quantum gates have to be represented by a unitary matrices, then only you can show the norm preserving from left to right in the operation of quantum states. Okay, right? So that is a one serious conclusion you can draw with a single qubit NOT operation. Okay, right? So let me go for the next possible single qubit gate. Okay, so far we just saw a quantum gate which just reverses the places of the probability amplitudes alpha and beta. Okay, so what else I can do? I can do something more here. What is that is, alpha and beta are of positive parity, means there are positive signature. I can change one of them by introducing an extra negative parity between alpha beta by adding a negative parity to one of them. So what is that? Let's say I have alpha beta column vector. I can make that alpha beta column vector as alpha minus beta column vector. You know why I am thinking in this direction? Remember, I can't change the length of the norm of the vector, but I can introduce some internal rearrangement, but not length. So I am not allowed to play and come up with any sort of combination of alpha beta. Okay, only thing is alpha square plus beta square must be 1. In that direction, one thing I can introduce a change here is, let's introduce a minus sign for beta. In that way, the norm is still preserved. Okay, right? So if at all, if that gate is there, if at all that matrix operation is there, which converts alpha beta to minus beta, is a kind of a unitary matrix which is represented as a 1 0 0 minus 1. Okay, so again, if you carefully notice this Z matrix, or it is called as a Z gate or a Z matrix, if you carefully notice, which is actually a unitary matrix, means Z multiplying to Z as adjoint is going to be unitary matrix. You can please cross check later. Okay, right? So fine. Now, what else I can do? I can combine X gate and Z gate, come with the Hadamard gate, like it's something called a H gate. Okay, what is this H gate does is, it pushes the quantum system from the ground state to a superposition state, equal superposition state. That is a H gate for you. Earlier I was showing you on the block sphere representation, a quantum state initially pointing along the along the North Pole, becoming a superposition along the x direction, is actually an action of Hadamard matrix. It is an action of a pulse being introduced or a pulse being punched onto a quantum qubit state in a zero ket state to become a superposition state. It's like a atom strictly in the ground state initially. When I introduce a pulse having pi by 2 area onto it, what happens? A quantum system becomes a superposition, means electron does an oscillation between ground and excited continuously. That is a superposition state for you. That is a being created out of a Hadamard action. That is what's shown in the one of the gate operation. So H acting on 0, giving you superposition of 0 and 1 with equal superposition. What is the equal superposition? 1 by square root of 2 is an amplitude, probability amplitude, and 1 by 2 is a probability. Okay. And interestingly, if you just notice, if you act H on 1, again you get a equal superposition of 0 and 1. This time the quantum state is pointing along the negative x-axis. Okay. What I mean is, go back to the block sphere representation. Let's say initially quantum state is pointing towards the south pole. Now if you act a pi by 2 pulse onto it, what happens? The quantum state is going to rotate about the y-axis, going to line for the minus x-axis along this direction. So that if I align to the minus x-axis, what happens? The quantum system is going to be 0 ket minus 1 ket divided by square root of 2. So that is the action of Hadamard on the 1 ket state. Now the question is, how do I represent mathematically? I have a quantum state, ground state 1 0. Okay, I want to make it a superposition state of 1 1 equal. Okay, so what should I do? I have to have a matrix which is a sum of x and z with some scaling factor of 1 by 2. I just have earlier x gate is 0 1 1 0, and I have a z gate 1 0 0 minus 1. If I sum them, I'll get some matrix. In order to have a matrix being unitary, I need to multiply a factor of 1 by 2. Now if you see, if I have such a matrix, if I add such a matrix on a single bit state, it becomes a superposition state. So in a way, you can say innovatively H gate is being arrived using adding two gates. One is X, another is Z gate. Okay. So this is a Hadamard gate for you. You can cross check whether Hadamard gate is unitary or not. It is of course unitary. That is why we have put 1 by square root of 2 to make X plus Z as a unitary gate. Okay. So you can cross check that. Fine. So far we have seen 3 gates. One is X gate, another is Z gate, another is H gate. Okay. So there is something called right. Okay, there is something called Y gate. So Y gate is just like a X gate, but is just like a X gate. Instead of 1 1, I'll have I here, complex I here at the bottom, and in the top we'll have minus I. So it is a Pauli matrix Y. Okay, using a Pauli matrix Y, we can construct a Y gate for you. In fact, if you notice, what is the action of Y gate? Action of Y gate is combination of X gate followed by action of Z gate, or Z gate followed by X gate. So Y gate is, in a way, it's an effect of both of them, X and Z. Okay. So as an assignment or something, you can just check what is the Y gate operation. And remember, Y gate is also unitary by nature. Okay. right? So on a two-dimensional surface, if I want to represent, not on a block sphere, on a two-dimensional surface, if I want to represent, let's say my x-axis is 1 ket, okay, the positive 1 ket, negative 1 ket. My y-axis is, sorry, positive 0 ket, negative 0 ket. My y-axis is 1 ket, my minus y-axis is minus 1 ket. If that is the situation, the combination of both of them would be along the first quadrant of this unit circle. Okay, so which means I can rotate the quantum state from 0 to a superposition of both by simply about this axis of this surface. I can rotate the quantum state. Let's say initially it is pointing along the 0 ket, later it can become 0 ket and also 1 ket. Okay, so basically you are rotating a given quantum state about some axis is a quantum gate operation for you. Even the Hadamard gate operation is also the same. Okay, right? So Hadamard gate is a bit confusing. Okay, so please don't get confused. If you just see from the block sphere representation, if the quantum state is pointing along the 0 ket state, in order to make the 0 ket state to become a superposition of 0 and 1, I have to rotate that quantum state from north pole to equatorial plane. How about some y-axis? So this is a x-axis, y-axis. The x-axis towards us, okay, pointing towards us from the screen, and our right side is an y-axis. Okay, top direction is a z-axis. Now the quantum state is pointing along the z direction. In order to make it to point along the x direction, what I have to do, I have to rotate towards me. So it is pointing up, I have to rotate towards me. I have to rotate by pi by 2 angle. When I do that, the quantum state being a single bit state becomes a superposition state. That is a pi by 2 pulse action in the experimental lab. So that is actually Hadamard gate operation, which converts the 0 ket to 0 plus 1 ket divided by square root of 2. It's a quantum qubit state process. Okay, so quantum qubit state process, that is what showed here. Okay, right? So next thing. Okay, so single qubit gates, you can think of very simple 3 qubit gates. One is X gate, Z gate, and H gate, and there is a Y gate also. Okay, and if you carefully notice H gate, Z gate, or a Z gate, you can take a square root of a Z gate and you can define something called a T gate. Okay, a T gate is a square root of a Z, and then you can take a square root of a T gate, you get a S gate. Okay, so basically it's like a phase operation. You are introducing a phase operation. What I mean by phase operation is, if you notice a Z gate operation, what it is doing, it is introducing a phase of exponential I into pi radians to the 1 ket. So what is exponential I? Exponential I into pi, it's a minus 1. So it is introducing a pi radians of, okay, completely out of phase, like a 180 degrees out of phase between 0 to 1 ket. It's like the 0 ket and 1 ket are flowing together in the same direction. Suddenly Z gate flips the beat 0 1 ket to go in opposite direction. So now both of them are going in opposite direction. So that is what the phase of two bits changed completely, like out of phase they become. So that is 180 degrees out of phase I can introduce. I can introduce any other than that, some other angle of out of phase. So what is that? Square root of a Z gate will introduce what? It will introduce exponential I pi by 2 phase change for the 1 ket. So in that case, what I will see, exponential I pi by 2 means iota I will get, okay, when I introduce a square root of z gate action on the quantum state. That is 1. Let's say I'll introduce a square root of z gate, that is a t gate operation. In that case, what I'll get? I'll get an exponential I pi by 4 phase introduction between 0 ket to 1 ket. So those are the few more single qubit gates which are actually the updated version, some kind of a manipulated versions of the Z gate. So S gate and T gates are those gates. Okay, right? The fundamental gates are X, Y, and X and Z only, and Y is a combination, means repeat action of both X and Z in one place. That is a Y gate operation. X and Z gate sum it, and you create a new gate. It's a H gate for you. So more or less, X and X gate and Z gate are the very fundamental gates from that to we can generate all sorts of new gates. Okay, right? Fine. So that those are the single qubit gates for you. Okay. Now there is something called a multiple qubit gates. Means anything other than single qubit, multiple qubit gates means the gates will take two inputs, okay, and process the two inputs. Unlike a classical operation, classical gates where two inputs are taken, and you see this is the classical gates, two inputs are taken, only one output is generated. Except a NOT gate, you see all the other gates, AND, OR, NAND, NOR, XOR. In all those cases, you see multiple inputs, single output. So what you notice is the information of the input is destroyed and output is generated at the cost of destruction of the inputs. Okay, so the reversibility is not there in a classical operation. Means I can never go back to the classical operation and get the input from the outputs. So that is the very important difference between the classical gate operations to the quantum gate operations. Okay, so having noticed that, let's go back and see the two qubit gates, multi-qubit gates. Somebody was asking, okay, it's like a registers, many information carriers going through some kind of optical fiber. So there is a one qubit going on the top, there is a second qubit going on the bottom. I can have X and Z gate or H gate on each individual, but I want to have more than that. What is that more is, depending on the control, there is a control signal is there. Depending on the control signal, I want to do something to the target signal. So that is what my target. Okay, that is what my objective is. So for me, a C NOT gate means a control NOT gate does the job for you. What is that? There is a control operation. Depending on the control, target is going to be flipped. As usual, my quantum gates or quantum states are going to be zeros and ones. Let's say I take a control is 0, target is 0. I'll choose my gate in such a way it is not going to have any effect on the target because my control is 0 in this place. Okay, doesn't matter. I can have a target of any kind. I can have a target to be 1 or target to be 0. Since my control is 0, I will not have any effect on the target, so that whatever is input is given, same output is coming out. Let's say such gate is available. Okay, and another option I will be needed to have here is, whenever I control is 1, means control is high, target must be flipped. What is the flipping action? A target, whenever target is 0, should become 1. Whenever target is 1, should become 0 for a given control being in the high state. Okay, so that is the C NOT gate operation which I would be needing for a controlled NOT operation or for a multiple gates. Okay, right. So let me write down a kind of a truth table for this kind of a requirement. Okay, so what I am doing, all the controls are either low or high. Whenever it is low, what happens to the target when target being 0, 1? It remains to be 0, 1. Whenever control is 1, target must be flipped from 0 to 1, 1 to 0. Okay, so in this case, if you notice, the control just goes as it is, not bothering anything in the processing. So control, whatever control I'm giving comes out as output. Only target going under some change. Okay, this is a truth table for you. If you carefully notice what is the target output, it is actually 0 addition modulo plus 1. That is the effect. What you are seeing is 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, because I am talking about addition modulo 2. So if you look at this truth table, it is a XOR operation for you. So the question is, if at all, if there is any control not operation which I want to have this effect, it should act like a XOR operation in the classical gate operations. Only thing is, in addition to XOR output, I also should get a output of a control signal. If that is there, it's like control signal, control also comes out, then my XOR operation is a control, not quantum gate operation. Okay, right? So this is what required. When I want to have a quantum gate operations, if you recollect, all the quantum gates must be a unitary gates. Now a quantum quantum information 00 gate or a 01 gate, a 10 gate, 11 gate could be represented as a column. Okay, so let me show you what is that column representation could be like this. Okay, if you see 00 ket means 0 ket tensor product of 0 ket. Okay, what we will get? 1 multiplying onto the two entries, you will get 1 0. 0 multiplying onto the second two entries, you will get 0 zeros. This is how tensor product is defined for higher dimensional quantum systems. So 0 0 is a 4 element quantum system, and so on other 3 elements. So when I have a control gate acting on one of them, I'll get some other output which is also 4 by 1 column vector. Okay, right? So the question is, if at all, if I have a control not operation which acts on 0 0 ket, gives me 0 0 ket. If it acts on 0 1 ket, it gives a 0 1 ket as it is. If it acts on 1 1 ket, it must give you 1 0 ket. If it acts on 1 0 ket, it should give you 1 1 ket. If you see, this is the 1 1 ket for you. Okay, so by trial and error method, you can always guess what could be the matrix for such an operation. Remember, the gate representation for that matrix would be a 4 by 4 matrix. You know why? Because I am playing with the 4 by 1 dimensional quantum vector, which means the matrix operation must be 4 by 4 matrix. Okay, so if I divide the entire matrix into 4 parts, like a first quadrant, second quadrant, third and fourth quadrant, if you see, first and third quadrants are parts 2 by 2 matrices, and the second quadrant is identity, and the last quadrant or the fourth quadrant is a X gate. Okay, so what matters is the diagonal elements as a diagonal quadrants. The first quadrant is identity, nothing should happen to the control, and target must be flipped, that is done by X gate. Okay, so that is how the control NOT gate could be understood in a matrix way. When it comes to representing on the paper, a gate operation is represented by a dot followed connected by addition modulo X operation with a line. So this is a C0 gate operation for you. What it mentions is a target B is manipulated by adding a control with addition modulo symbol. So that is an operation output for you. Control remains as it is, same form, but a target gets flipped up by adding a controlled value with the addition modulo, additional modulo operation. Okay, right? Okay, so will you share this PPT at end of the class? Yes, definitely. I'll be sharing it. Okay, right. So let me go for that. Control not gate operations. Okay, and if I carefully notice just now, like I iterated, classical gates are not reversible. Quantum gates are reversible. You know why? If you multiply a quantum operation twice, matrix wise, you are going to get identity matrix. They are unitary by nature, which means if I feel that quantum gate is not working for me, I want to get back my information again. What I can do, I can simply add the same gate operation and the same output and get back to the input state. Okay, right? Okay, so let me go. Now, playing with the multiple gates. Okay, Hadamard gate we just saw, it creates a superposition. C0 gate is some kind of a NOT operation with a control. If I combine them both, what it does, it is going to create a beautiful effect called entanglement. What is this entanglement is? It puts the two qubits, initially they are starting in 0, 0, single bit state, to become a superposition state together in such a way, right? They become a quantum superposition states in a quantum mechanical form. Remember, physically they can be separated by intact, by keeping their quantumness intact. We can separate them when I put them at two different places. Okay, two different places, all the way separated by distance. In that case, you do something with the one of the system will induce whatever change the one of the system is going through, same change will be induced on the other system simultaneously. So that is the entanglement for you. It's like two things are so into each other. Even when they're separated, in that case, some change going on here will also goes in here without any time delay, as if both were same persons responding to the same scenario. Even the action is happening in the one of the situation. So a combination of quantum gates, one is single qubit H gate, another one is two qubit C0 gate, together is going to create a superposition state, which is an entangled state. Okay, so somebody is going to introduce for you the detailed what is the entanglement and how the entanglement going to help you to do some advanced quantum protocols. Okay, right? Fine. So C0 gate is there. What I can do with the C0 gate, I can play around. Let's say I take three C0 gates. So one is control at the top, bottom at the target. Next one, control at the bottom, target is at the top. Let's say I just interchange the order of control and target for the three C0 gates. Okay, and I send some input at the top, input at the bottom, and if you notice what is the input and output at the very last, you see the inputs are swapped, the quantum states are swapped. So this is called a swap operation. How can I realize this? I can realize this swap operation by putting three C0 gates in opposite order with their control and target order. Okay, right? So a swap operation is a very important when it comes to realizing a very lengthy quantum network. Whenever there is some problem with the connectivity between the very extreme qubits, let's say, then I can swap the qubits so that I can bring in the extreme qubit information to very close and do the operation and then go back with a swap to the extreme situations, okay, different positions. Okay, right? So it's an optimization task for you there. Will probably somebody will be discussing in detail. Okay. All right. One more important thing with the classic quantum gates is even you can realize a classical gate operations using quantum gates. For example, you can have AND operation. Okay, you can have a fan out operation, means you can replicate a single bit state, not a superposition state. See, y is a single bit. I can replicate a single bit state to two single bit y states. If y happen to be superposition, I can't do that. It's impossible. That is called a no cloning problem superposition in the case of quantum systems. Okay. For example, in order to realize AND operation, what should I do? I have to use two controls and one target. So two controls can be A and B, target can be C. And now if you see, if I introduce C to be 0, what I will get at the output A and B. In that way, I can realize the AND operation for classical realization with a quantum gate. It's called a Toffoli gate. Toffoli in the sense two controlled, one target. Okay, the same Toffoli is useful for replicating a single bit states in multiple scenarios. Okay, so this is a no cloning theorem for you, which tells me it is impossible to replicate or mimic a quantum state from some superposition to multiple similar kind of a superpositions. If I assume that, I will be getting some kind of a result. If I see in reality, a C0 gate is the closest, the first hand quantum gate, which does kind of a mimicking or a replicating effect in the classical gates or a classical operation. Similar thing is a C0 in the case of quantum gates. If I see in reality, I'll get some output and compare the approximated output, which is based on cloning is possible. From that output to the actual scenario, you would be getting some equations which has to be satisfied to have a cloning, okay, which are going to give an absurd result. That's why cloning is concluded to be impossible in the case of quantum systems. Okay, right? So that is a quantum single bit and multi-qubit gates for you. And in the later part of this session, we will discuss something called Solovey-Kitov's theorem, which allows you to realize a given quantum state or a gate operation using the simple fundamental gates. Okay, right? So what I will do now, I'll quickly give a break for 5 minutes and then come back maybe at 6:20, 4:20, and then we will continue the remaining part. Okay, so we'll discuss the questions after that.
Right, sir. We will take a break and come back. Sir will join at 4:20 and we'll continue. Right. Meanwhile, for those who are having some questions, which I can also answer, will you share the PPT at the end of the class? Yes, all the lectures will be shared. All the slides will be shared, including sir's class written notes will be shared, right? Enter electrical engineering background. Maybe that's why these brush up courses were there, QT-01 to QT-05. Of course, you can look into the videos if you have joined this course. Again, we are covering the basics like gates today. Sir was discussing some quantum concepts also, sir has referred again. So you can refer the videos related to these content in the earlier course QT-03, QT-02, where the basics were discussed. And you can try to look at that, right? So at the same time, yeah, books, any book that you can start is, there are a lot of books on this thing. What do you say? Quantum computing. Nielsen book is there to start with. There are a lot of slides and material also, which we will share shortly. So you can try to look at that. The classes will happen from 3 o'clock to 5 o'clock every day, Monday to Saturday. So these are some queries that were there. So I have answered. The remaining questions, sir will answer. Yeah. एक बार देखना ऊपर कोई चार्ट है. Yeah, list of books we'll prepare and place it on canvas. Yes, we'll give that. In fact, yeah, in the previous courses also, many people have referred a lot of books. We will make a list of those things and make it available.
Yes, everyone. Yeah, I will just try to connect the tab. It is creating some issue. Okay. Yeah. So what I'll do, I'll just confine to the PPT. But don't worry, the PPT is shared. Yeah. So there were questions here. I hope you can see the screen. You are seeing the screen, right? I'll just try to clear the questions here. Okay. Right. When it comes to a background of electrical engineering, very new for physics, these mathematics equations are involved. So the Jagdish ji is asking, is there any book which is suitable for understanding even from electrical engineering background? So the book by Nielsen and Chuang, it discusses linear algebra for one full-fledged chapter. So that is enough. With just a matrix algebra understanding from our 11th and 12th standard, you can understand that entire chapter, and that is a background for entire quantum computing. So you please go through that chapter of that book. It's straightforward. Okay, right. And Chaudhary ji is asking, what is the use of fan out operation? Okay, if you just see the fan out operation here, okay, so there is a Toffoli gate, means two controls, one target, and both the controls, one control is taken as 1, another control is taken as y. Y can be either 0 or 1. So suppose I want to replicate 1. Okay, if I replicate 1 to multiple outputs, what I will do, I'll take y is equal to 1 and ancilla. This is something called ancilla. It's like by default, I will take the third target as 0. So what I will see, I will get two outputs. Both are in the same state. It's like a replication effect, not a cloning. It's a kind of a single bit being replicated multiple times. It is just like tapping in the information in our classical communication. You just connect two wires. Back then, if some two parties are speaking on a phone, you just connect in between a tap signal. So you see, you can hear that. Okay, right? So, but when it comes to quantum superposition state, this is not possible. If y is a superposition state, I can't replicate. So fan out operation is like a series connection in a classical electronics. Okay. When it comes to applications, there is no quantum application as such here, but just to show that a classical tapping information could be done with the classic quantum gates, that is using Toffoli gates. That's why it is shown. Okay, right? Okay, then there is a question. If I have a 3-level system, I would need 3 qubits to define it. Yes, 3-level system means 1 qubit, second qubit, and the third qubit. 3 qubits are going along parallelly. Okay, how to formulate this into Q-trait? Q-trait means what? It's an extension of the qubit. When I see what is my qubit, let's show you what is a qubit for you. Okay, so qubit is psi is equal to alpha 0 plus beta 1. What will be the Q-trait? Q-trait will be alpha 0 plus beta 1 plus delta 2. So there are 3 states, 3 qubits parallelly traveling, or 3 channels parallelly traveling, okay, or one channel being existing in 3 states like a 0, 1, 2. Okay, so that is a Q-trait for you. But when it comes to 3 qubits traveling, means each can be of any type. Okay, so please separate two things. One is quantum qubits traveling, another one is quantum qubit or a qubit having multiple states. Q-trait is having 3 multiple states. Okay, so slightly keep the two things separately. Qubit means multiple D state system. In that, D becoming 2 is going to give you a qubit. D becoming 3 giving you 3-dimensional quantum system is called a Q-trait. But when it comes to information processing, here you see there is a 1 qubit going, another qubit is going, but initially 1 qubit being put in a 0 state, other target is also put in a 0 state. This is not always required. Once you keep processing inside your quantum circuit, later stages in a given quantum channel, you may have superposition state, not a single bit states. Okay, right? Okay, so let me go further. If there is any question, Durgeshji, please separate the understanding of Q-treat means Q3 level quantum system from information traveling as a 3 qubits. Okay. Yeah, you are right. It's a 3-level system, but it is different from qubits, 3 qubits traveling. Okay. Right. Okay. So there is a question. How gates are made physically? Very good question. How gates are made physically? Like I was showing you earlier, you see, superposition state is created by, okay, is created 5 by 2 pulse. Okay, just a minute. Where is that block sphere? You see, superposition state from 0 bit is created by pi by 2 pulse. So physically what people do is in the lab, they're going to create a pulse of lasers. Those pulses of laser go and interact with a two-level atomic system. Initially, the atomic system may be cooled to sub-zero, where atom may exist in the ground state with an electron being in the ground state. When that pulse of photons comes and puts the electron to go hopping between 0 and 1 continuously, it's called Rabi oscillations. That is a superposition state for you. So a action of pi 2 pulse onto a quantum qubit and an atom in a ground state is a physical realization of gate operation. Okay, so there is other way when it comes to photons. Let's say photon is in the ground state initially. Let's say it is in the single polarization state. I want to create a superposition polarization. So I will have some material like a quarter wave plate which rotates the quantum polarization of a photon to some diagonal polarization. Okay, right? So there are also something called a beam splitters. So they split the beam into multiple dimensions, like yesterday was saying. So in this way, you can create a superposition state, like a Hadamard gate operation. If I want to convert 0 to 1, 1 to 0, what I'll do, again, I act with the pulses only, like of single photons or continuous stream of photons. Okay, so gate operations are realized using the energy, the way energy is supplied to the system. Using that idea itself, gate operations are realized. Okay, right? Any other question? So wait a minute. Okay, could you please tell me from what time to what time the classes will happen exactly? 3 to 5. Already answered. Okay, books, I think. Okay, for a Q-treat, the only gate operations which we have seen so far is a Toffoli gate. There is no other gate, the fan-out operation. Okay, right? How far it will be helping in computer science background students? Okay, so yeah, you please check Nielsen Chuang. The one of the chapter on linear algebra gives the mathematics, and a very introduction. First chapter itself discusses the overview of the entire book. Okay, so first 3 to 4 chapters, if you can cover, that is a very good initial start. Okay, so what is the entanglement and spin motion relationship? Okay, so two them, put them into entanglement in such a way, even after you separate them, I do something with the spin system, the other system also changes. So that is an entanglement between two spin systems, or two spins of an electrons can be put in entanglement and separated also. Physically can be separated, but quantum mechanically they can be in the entanglement. Okay, and I can do something here, some change can be seen in some other place. So that is a quantum entanglement effect for you, and it's also called a spooky action at the distance. Definitely, this is an elaborated version of the entanglement will be discussed somewhere later in the applications of quantum computing. Okay, right. Okay, so totally how many quantum gates are there, out of which how many are universal gates? A very good question. So the single qubit gates, X gate and Z gate. Is there any other gate? Is actually a upgraded version or a combination of all these two gates. H gate is created out of X and H summing, and a Y gate, action of X followed by Z gate, or a Y Z gate followed by X is the Y gate with some kind of a phase addition. Okay, right? So, and there is a S gate, there is a T gate. Okay, square root of Z is T gate or S gate, and square root of S gate is a T gate. There is something like that. And there is a X gate. You can take a square root of X also. Okay, so that is also another gate. So likewise, there are multiple single qubit gates are there. More or less, all of them are constructed out of X and Z gates. Okay, when it comes to qubit gates, C0 is the fundamental gate, and probably fully gate is also the fundamental gate. So from these, other gates can be constructed. For example, there is something called controlled unitary gate. It's a two qubit gates. I can also multiple control one unitary gate. Okay, so that is another gate. So basically, these are like spin-off versions of all the gates which we discussed. Okay, fine. So that is about the gates. So let me go to the second part of the session today, which is called Solovey-Kitao's theorem. Okay, let me slide show. Okay, right? Okay, let me exit the slideshow here and go to presentation. 1 minute. I just want to see if there is any chat messages in between. Okay, just a minute. Yeah. Okay, now I'll do a slideshow. Okay, so Solovey-Kitao's theorem. What is this theorem says is, there is an efficient way you can realize any quantum new gate using the known fundamental gates. Just like if you notice in a classical computing, the universal classical gates are there, NAND gate and NOR gate. Using them, I can realize every other gate. Okay. Similarly, the quantum gate operations is nothing but processing the quantum information from some form to other form. This transformation of some form to other form is a gate operation. Probably this gate operation maybe we don't know straight away, but we can do what we can do. We can show that this overall gate operation is a combination of some known gate operations. Okay, right? So coming, let's say there is a Bloch-Speer interpretation of gate operation of rotating a quantum state from one form to other form. It can be seen as rotating about X gate, rotating about Z gate, rotating about Y gate. Okay, a combination of all of them giving you one gate operation. Okay, so that is what the Kitao's theorem says. There is always an efficient way I can realize oral gate operation, okay, by using some known gates. It is called a set of gates. It's called a Clifford gates. Okay, so what is the Clifford gates are? Clifford gates are something to do with, let's say you take a poly gates, X gate, Y gate, and Z gate. Okay, you do some manipulation with the X gate. Okay, you multiply H on both sides. Okay, with one of them is adjoint H, other one is H. If you multiply a X gate with the H on both sides, you will be getting a Y gate on the right hand side. Okay, that is like some kind of a conjecture, like a going from polymatrix to polymatrix operation, like doing something with the polymatrix, reach another polymatrix. Like do something with X, you get Y. Do something with Y, you get Z. So there is always a one-to-one relation of conjecture is there. Okay, this conjecture is possible with the gates like H, T, and S. So these are belongs to the Clifford gate family. Okay, so using these gates, what can be done is any required unitary gate can be realized or converted into a individual small Clifford gates. So those small Clifford gates together is going to allow me to realize a required unitary gate. So that is what the Solovey-Kitov theorem says. And here the problem is, let's say you want to have a rotation about x-axis with some angle of 0.8 radians. Okay, 0.8 radians. I want to rotate a given quantum state about the x-axis with some angle. If I want to rotate about 0.8 radians, I want to have some unitary gate. Okay, but that unitary gate I don't know. That's a rotation gate. I don't know. What I can do is, using the known gates of Clifford, I can realize that rotation. But the problem is, the known gates are not like completely allows you to realize any gate, any required unitary gate, right? Up to some extent, you can realize that. Let's say rotation about 0.8 about x-axis can be realized up to some extent. What extent? The error can be of the range 0.0, it's like a 0.001 range. Up to that extent, we can realize that unitary gate operation. That is Solovey-Kitov's theorem says. For example, let's say U gate is the required for me, but I realize some G gate using Clifford gates. What is the difference between them? The difference between them will be like in the determinant case, if I take a U minus G determinant, how different they are, and they find the determinant of U minus G, it is much less than 10 to the power of minus 3 or close to 10 to the power of minus 3. That is what the one of the possibility Kitov actually says, Kitov theorem says. Okay, and now this, how many gates are required to sum them up to create this unitary gate? That is also of some order. Okay, so that order is given as some log of in terms of the epsilon, which is 10 to the power of minus 3 here. Okay, right? So the Kitov's theorem says, Solovey-Kitov's theorem says, definitely we can realize, but some extent of error would be there. Okay, so let me go further. Okay, so here there is a formal statement. What it says is, given a universal set of G, okay, and a unitary U, right, in a SU2, SU2 stands for unitary gates of order 2. Okay, so there exists a sequence of gates from G2 approximating U within an error of epsilon. That's what I was saying earlier. Okay, right? And the sequence length scales as the number of products, number of elements in the products scales as this, where C is in the range of 3 to 4. Okay, log to the power of C, right? Okay, so one simple example, if you take, you will understand. Okay, so before going to this example, let's see why is this theorem important. Okay, in fact, this theorem bridges the algorithms with the physical quantum hardware constraints. Okay, right, and this algorithm allows use of finite gate sets to approximate any gate operation. Obviously, right? Any quantum gate operation can be realized using known gates. Okay, and foundation for practical quantum compilers and quantum synthesis is possible using this Kitov's theorem. Okay, right? So that is why it's very important to know this. So one simple example I was showing you. Suppose I want to realize a rotation about 0.8 radians, that is what? 45 by 84 rotation around x-axis. Okay, that is what I want to know. I want to have. Okay, what is the corresponding representation on paper, you see, rotation about x-axis with a theta angle means what? Exponential of, if you see rotation matrix, you can always construct using x gate. About x-axis means x gate operation. How did I get to know this? You use the block sphere representation. From there, you can write this rotation matrix. Okay, right? So the rotation matrix about x-axis means exponential I theta x. Sorry, theta by 2x. Okay. Now theta is what? 0.8 radians. So you substitute that 0.8. What you get here is, okay, the result would be, if you want to convert it degrees, it is 45.84 degrees. So if I have to realize this rotation gate, I would be gate and a T gate and a H gate. Okay, so let me show you that. What is the H gate for you? Hadamard gate. What is the T gate for you? It is a root of Z gate. Square root of Z gate is S gate. Square root of S gate is T gate. So T gate is a Clifford gate for you. H gate is a. What I will do? I multiply H with. Interestingly, I am going to get Rx with an angle of pi by 4. What is the pi by 4? 45 degrees. 45.84. What is the difference? There is a 0.84. So I want to have 45.84 degree rotation, but HTH is going to give me pi by 4 means 45 degrees rotation. It is going to give. There is a small error is there. That is obviously coming from this. Okay, so you can cross check. First, if let's see, multiply H with a T, you get some matrix. HT with another Hadamard matrix, you are going to get a U matrix. Okay, so this is some unitary matrix. Now you take that unitary matrix, okay, right? And if you approximate in terms of rotation about some global phase, what you are going to get? 15 pi by the overall result. So in terms of, okay, so in terms of where, okay, a pi by 4 angle. Okay, so this is a Kittov's Solovey theorem, Solovey-Kittov's theorem for you. Example, what you can do, you can just cross check some other example. Okay, and if needed, what I will do, I will add on Solovey-Kittov's theorem how to realize some random gate operations. Okay, so that could be one interesting exercise you can cross check. Okay, right? So yeah, right. So I did not share. I'm sorry. What you pointed out. Okay, so let me see up to what time PPT is not visible. T9. Okay, okay, slides are not visible. I'm sorry. Okay, don't worry. I will repeat that. I will repeat. Luckily, we have some time for to do that. Okay. Okay, so let me repeat it. Okay, so what did we do before jumping into the Solovey-Kittov theorem? We just concluded that, okay, universal thing would be Hadamard gate, would be CNOT gate, or X gate and Z gate, which are actually the fundamentals of all the gates. Okay, so using those gates, you can realize the higher order gates. Okay, right? And the next thing we discussed is Solovey-Kittov's theorem. what is that Solovay-Kitow's theorem is? Okay, wait. What is that theorem is? It required gate can be realized out of some Clifford gates. What are the Clifford gates are? So these Clifford gates, okay, connects poly matrices with each other. Okay, if I multiply poly matrices like X and Y and Z by some H gate on the either side with one of them being adjoint of H, other one is H itself, it is going to lead me X to Y. Similarly, Y to Z. It's like kind of a one-to-one between poly matrices to poly matrices. So this conjecture is possible with some Clifford gates. What are the Clifford gates? Clifford gates are H gate, T gate, and S gate. Okay, and S gate is a square root of a X Z gate, and T. So in fact, T is a square root of Z gate. Okay, so Kitov matrix or a quantum operation can be converted in terms of product gates. Which kind of multiple gates? The Clifford gates can be used to realize the. If I want to realize a gate operation about x-axis rotation with an angle of pi by 8 rotation, if I have to realize, what should I do? I have to use a Clifford gates multiple times action. Okay, let's say if I am doing it, it's G, which is very close to the required gate U. Now I just compare what is the difference between them. By the way, they are matrices. I can just see the difference between two matrices by element separation. I'll get some matrix. Now find out the determinant of that matrix. If the determinant of that matrix is 0, means I have a pakka one-to-one mapping. I realize the exact required gate. Otherwise, if there is some small element is slightly different, I'll have some determinant. If that determinant is much smaller than 10 to the power of minus 3, means I have successfully created to a very good extent the required gate. So that is what actually Solovay-Kitow's theorem says. It says there is a possibility to realize required gate operation using the Clifford gates to that accurate extent. Now, how many number of multiplications I need to do? That is a depth of the multiplication sequence, gate sequence depth or a length. How many gate operations will be required to just realize one rotation effect? Means how many times I have to multiply. Showing you here. Okay, let's say I have to rotate a quantum gate about x-axis with a pi radians 0.8 radians. Okay, so which is equivalent to 45.84 degrees, which is possible by take the vector, multiply with the h vector, multiply it with the h gate, multiply with the t gate, multiply with the h gate again. You are actually going to get that operation. Okay, h, t, and h. The resulting effect would be just a 0.8 rotation about the x-axis. That is the Solovay-Kitow approximation. In fact, what that view is, it is going to give you is a pi by 4 operation. Is that? Yeah, it is going to give you a pi by 4 operation, which is equivalent to 15 into. Okay, right? Is it 15 into pi by 8? You need to cross check. Maybe a small typo here, but more or less the idea is you can realize any given gate operation using the Clifford gates by taking them in the form. Right? So there is a global phase here. There is a. So global phase is not going to matter for you, remember, because whenever I take a global phase just disappears. Okay. Yeah. So whatever I discussed in last 15 minutes. Okay. Right. So Right. So probably I might come back to discuss few things with you people. That time, maybe definitely I'll be in my institute. Okay. So that time I can use both my hand notes and explain. Okay. There is a very good question here. What is a G here? Okay. Let me explain. There is, remember, G. Yeah. See, this is a required as a quantum gate operation which rotates a given quantum state about the 0.8 radians. Okay, that is required for me. But somehow I realize not exactly U. It is very close to U. What is that? It is that is a very close to U. How close? Some gate. Some. Now, what is that realized gate? How far it is from the actual gate? That is the U. Actually, is U. Realized difference of determinant of a difference is less than epsilon. The realization of the gate possibility with the Clifford gates. Okay. I want to prepare a dish. I have a raw material. With my inexperience, I'll not prepare perfectly because there is a hinge of less and more sauce. But I reach to the actual dish, actual recipe, 100% perfection. So how much error is there? That is represented as a less than epsilon. Okay. Right. So I will summarize for today. Right. We discussed about quantum gates. Before that, we discussed about what is this quantum gate representation in terms of how geometrical interpretation allows me to understand the change in the quantum state from one form to other form. Okay, so one form to other form it changes. Then I will okay, so I can use, right, I can use the PPT. Okay, one minute. Yeah, so one form about gate rotation or a vector notation. Any quantum gate undergoing a change means it is pointing out in a particular direction in geometrical interpretation. It is changing from that direction to some other direction. So the quantum evolution of a quantum system or a quantum change of a quantum system is all about rotating a quantum vector from one direction to other direction. That is a quantum gate operation for you. What kind of a gate operation? Qubit undergoing many changes like a NOT operation and operations like a phase operation, phase change, or quantum qubit being prepared from a single bit with the H operation, Hadamard. Quantum qubits undergoing some kind of a correlated change, it's a C0 gate operation, and two controls inducing a change in the third qubit is a Toffoli gate operation. So those are the single qubit, multiple qubit V gates which we discussed. Okay, a combination of gates would allow you to realize a kind of interesting effect called entanglement. Okay, and in life, how the gates are realized, like a punching a pulse of energy onto an atom. That is a Hadamard gate operation or a NOT operation, like a Z space flip operation. All those the gate operations. But remember, exactly you can't realize all kinds of gates. Only go to certain close percentage, like a 99% accuracy. So that is actually given by Solovey-Kitao's theorem, which says quantum gate realization only possible up to some extent. Okay, so what is that is, if I want to rotate, if I quantum vector for about an x-axis with a theta angle, what I'll do, I'll just simply take known gates of H, T, and head. I realize that. But how close is that? We have to see. So interestingly, that is next step. Okay. So that is a overall thing for you. A Silovikita and single qubit and multiple qubit systems. Okay. Right. So fine. Thank you very much for your attention. Sorry for having technical network issues here. I was not allowed to use handwriting, so it is in a way constraint for me. I'll share my PPT, and also I will share my handwritten notes, whatever I did so far. And I will also share some problems on the Kitto's theorem so that you people can understand in detail. Okay, right? Fine. So don't worry. More or the less, whatever things discussed today will be definitely will come here and there throughout this QT-05. So in that way, it will make complete. Okay, right? Okay. There is, if possible, please can you post some information in WhatsApp group and about the Canva? Okay, I think Pili sir will take care of that. He will, yeah, he will help and how to open the material, all those things. Yes. Okay. So thank you very much for listening and bearing with me despite having the network hiccups. Okay. Fine. Organizers. Satya sir.
Thank you so much, sir, for this wonderful session. And thanks to all the participants. So we will meet again tomorrow at same time, which is 3 p.m. So
Yeah.
once again, thanks to all. And
To
thank you
me?
so much, sir.
Yeah, I will share the material to that. Okay, so there is one question here. Sir, may I know biology students get benefited with this course? I mean, any particular quantum recommendations? Definitely. There are two avenues where quantum computing is taking a big strides. One is quantum communication, another is medical applications. Properties like a protein folding, the options of protein folding. Okay, it's a very, very important topic in medical field. So understanding that various possible protein folding is a very big optimization or so it requires a lot of data processing, a lot of memory, a lot of processing. So that is to a very good extent. So that's why knowing quantum optimization or quantum information processing is going to help. So I would really appreciate biology people coming in here and trying to understand. Okay, so in a way it has some kind of a maths, but don't worry, it can be easily picked up. Okay, right? So that is the answer for you. Definitely, biology students should come and go through this course. Okay, right. Okay, very fruitful session. Thank you, Bhaskar Reddy sir. Thank you. Right. I think Prashant sir is saying I'm a dedication in dentistry. Yeah, it's a very interesting, sir. Prashant sir, the first time I'm is coming into this course. Definitely, sir. Like I said, is there when it comes to drug design. It is there. Touch. For example, you people, dentists, are doing a marvelous job of coming up with artificially made dental implants, right? Okay, so the best implants, best artificial tooth, all those things the manufacturers are going to make, which is should not harm the body, should gel with the body. Okay, so it's a foreign material, should adjust with the actual human tissue. Okay, so for that there should be a possible combination of interaction, no interaction, and a very good gel between foreign implants with the tooth or tooth the holes, right, with the gums. So you can think about studying finding a better implants, better combination of material for the implants. Okay, so those things you can think about as a one of the application from the medical direction for a quantum computing. Quantum computing would allow you to see various possible scenarios. Okay, right? So the quantum applications would be that finding a better material to make the dental implants. Okay, so people are checking for a very good drugs. So drugs is, let's say, it comes into the field of medical application. When it comes to dentists, so you would be using a lot of like implants or I'm amateur in this field, but you would be knowing exactly. So to come up with a better choice, you need to explore various combinations, infinite combinations, I would say. So when it comes to quantum computing, it will be very, very helpful. Okay. Yeah, I will definitely provide all the material in the Canva. Since I don't have a common platform where I can share, that's why I did not do. If the moment I get the Canva link, I will be doing that. Don't worry. Okay. So this is the second class only. As time progresses, you will get to know everything. Okay, for learning quantum computing, yesterday also I was pointing out, somebody was also shared with a book called Nielsen and Chuang, Quantum Information and Computation Theory. Okay, it's a thick book. Don't worry, it's a very thick book. But if you study first 3 to 4 chapters, not more than that. Okay, you will understand the essence of quantum computing for the fundamental level. For application level, you have to complete the entire book. Okay, right? Yeah. So biology people also can easily go through and understand. Yeah, spell the book name. Let me do that. Okay, what this? I'll just share the link. What is there? Okay, Nielsen and Chuang. Nielsen and Chuang. Okay, it is freely available on the net, by the way. Right? 1 minute. I'm just searching the link, suitable link. Okay, let me give you a Wikipedia link. It has everything. Yeah. The book name is that. If you want a spelling, okay, Nielsen and Chuang, Quantum Computing by. These are the authors. Let me give the author names. Yeah. And a downloadable link, let me share. It's available for free, by the way. Nielsen and Chuang PDF if you search. Okay. And it is available. Okay, so I'm just sharing you the link. It's about 710 pages. You can just download. Please download this. Okay. Right. So like I was saying, how many chapters if you go to index, I'll exactly tell you which is important. Introduction and overview, first chapter. Okay. And introduction to quantum mechanics and introduction to quantum computer science. Okay. And quantum computation. If you have some linear algebra background, you can directly jump to chapter number 4. Okay, chapter number 4 is direct. Okay, or chapter number 4 is introduction to quantum computing. If you want some linear algebra, I would tell you to please go through some initial parts of chapter 2 and then directly jump to chapter number 4. Okay, right? And like I said earlier, if you can study up to chapter number 4 from 1 to 4, if you want, you can skip the computer science chapter, that is chapter on computer science, which is chapter 3. You can skip that. If you are not comfortable, then you can study 1, 2, and 4 is enough. Okay. Okay, there is somebody is asking here one more question. I am working on quantum machine learning problem. If data points are encoded in 4 qubits, is it possible to representation on block sphere? So how the data is represented in quantum? Very good question, sir. Rohan sir. Remember, block sphere representation is only reserved for single qubit representation. If it is more than single qubit, see, I need a 2 qubits means 4-dimensional system. Block sphere is just 2-dimensional system. I can't represent that. If I take 3 qubits, it becomes 2 to the power of 3, 8-dimensional. 8 dimensions I don't have in block sphere. If I take 4 qubits, it becomes 2 to the power of 4, 16 dimensions. Block sphere doesn't have 16 dimensions. So I need to get some other way of representing. There is something called a Q-sphere geometrical interpretation. IBM uses that. Okay, slightly confusing, but it allows you to represent a 2 qubit system, 3 qubit system, and 4 qubit, even 5 qubit system on a same sphere, but it's not like a block sphere. There is multiple dimensions can be represented on that, but it doesn't have a physical interpretation, but it's just for the sake of mathematics you can represent on that Q sphere. Probably if for you people, somebody is going to show you a quantum Qiskit usage on IBM experience. That time they will show you Q sphere, block sphere kind of a representation. Okay, right. Next question, Naveen ji is asking, I am project manager in mainframe software development projects. How this quantum computation course help me in software development projects? Any suggestions? Okay, suppose if you are going to process a huge amount of data, a lot of data you are going to process, you want to get the conclusions or the analysis in much quicker time. I would say using machine learning algorithms you are doing, you can convert the machine learning algorithms to the quantum machine learning algorithms, use some quantum hardware or quantum simulators, and you can do the more accurate prediction, more accurate analysis in much quicker time compared to classical computation. In your software development case, probably you can think about a kind of adding a quantum computing essence to that software, which in a way you can say it is much faster. Okay, so we are not reached at that final point yet, but definitely you can think in the direction of adding a flavor of quantum into your softwares, quantum processing. Okay, right? So any other question? Okay, no questions so far other than this. Okay, then I think we will wind up at this point. It's a 5:10 now. So thank you once again to all the participants. See you people sometime later in other sessions. Bye-bye, take care, and have a happy learning in the remaining sessions.
Thank you so much, sir, for this wonderful session. Thank you so much.
Thank you, sir. Thank you.